Hello guys, we have an interesting topic today, which is lecture 12, Determinants. So let me just remind you that if A is a matrix, for instance, A, B, C, D, then we discussed its determinant of A is equal to AD minus BC. Okay, so this is determinant of a 2 by 2 matrix, and this was from the first problem set, I guess, and it has a lot of interesting properties. Let me just remind you some. So one of them was that A is invertible if and only if determinant of A is not equal to 0. So determinant is exactly the quantity which helps you to see whether a matrix is invertible. So this is a really simple computational tool which helps to check that. So second property was that determinant of a product of two matrices AB equals to determinant of A times determinant of B. That's a beautiful identity. In particular, determinant of any power of a matrix equals to determinant of A power n. So this becomes, if you just think about it, as an identity between, some polynomials in A, B, C, D, this will be a very complicated, huge identity. So the fact that it always holds, and of course you just prove it by induction, is a kind of a miracle. So this is 1, 2, and maybe 3. Let it be it for now. So maybe property 3 is that determinant of A equals to 0 if and only if vectors AC and BD are linearly dependent. So that's the third property. And fourth property is that actually if you just take A, B, C, D, a pair of vectors in R2, then actually determinant of A is equal to twice, 1/2 determinant of A is equal to the area of a triangle 0, x, y. 0, x, y, maybe with absolute value here. So determinant is actually just nothing else but the area of a parallelogram formed by a pair of vectors taken modulo sign. And of course from here this property 3 becomes obvious because vectors are linearly dependent if and only if parallelogram is shrinked to a line. So it's basically area 0 case. So determinant of a matrix is something which generalizes all these properties to the case of arbitrary dimension. So let's suppose that we have A, which is now n by n matrix. So for all this story, it's very important that the size is a square. So matrix A is a square matrix. So it has n rows and n columns. And so then we will determine. So we will define determinant of A, which will be some element of the field. And there's really complicated long formula for this determinant, which I will explain a little bit later. And then it will have all these properties. So such that. So first one will be A is invertible if and only if determinant of A is not 0. Second will be that determinant of AB is determinant of A. Cats, stop that. Stop that. Sorry. Stop that. Determinant of B. 3 is okay. So determinant of A is equal to 0 if and only if columns of A are linearly dependent, and 4 is that geometrically determinant is related to volume. So basically the idea is that if you have n vectors in n-dimensional vector space, then you can think of them as you can define some parallelepiped in higher dimensions, and determinant is supposed to be something which is closely related to its volume. Of course, the last interpretation only exists for Rn, but we will talk about it at the end of the course. And the first and the third we will explain today, and the second is very important, but we will do it next time. So let me also emphasize that some people love determinants because this is something very concrete, very explicit, algebraic, with some combinatorial twist to it, and determinants appear beautifully in lots and lots of problems, combinatorial problems, computational problems, in applications everywhere. On the other hand, some people hate it because determinant is something very concrete, very algebraic. It's a huge polynomial, and proving something about determinant involves work with indices and so on. So I will try to explain to you why I feel that determinant is a very beautiful object in mathematics, and why you should not only appreciate its geometric meaning and abstract properties, which we will discuss next time, but also the exact formula, because the formula is actually remarkably beautiful. So and the plan for today's lecture is, first I will just define what determinant is, giving you a huge formula and explain how to think about it, and then we will start proving properties of the determinant which help to compute it. And at the end of today's lecture we will prove 1 and 3 and discuss some other applications of the determinant. Okay, so definition. So let A be an n by n matrix with coefficients in some field. Who knows which? Doesn't matter. So then let's suppose that A is given by this table A11, A12, A1n, A21, and so on, AN1, and so on, ANN. Perfect. So then determinant of A is the following sum. So let me write it down and then I will explain how to think about it. So we sum over all permutations sigma inside the group Sn. So here I have n factorial permutations and there will be n factorial summands. And then I write a product of elements A1 sigma of 1, A2 sigma of 2, and so on, AN sigma of n. And before this monomial, I write minus 1 power sigma. So let me explain that. So this probably does not need any explanation, just because this A1 sigma of 1 to sigma of 2, these are just some elements of the matrix. Minus 1 power sigma is, by definition, it is 1 if sigma is even, and minus 1 if sigma is odd. So depending on whether your permutation is even or odd, you get minus 1 or 1 terms. Okay, so before doing anything, let me just start with example. So if n equals to 2, then we have A being A11, A12, A21, A22. And then there are two permutations. So there is sigma equal to the identity and sigma, which is just 1-2 transposition. And so this will have two terms. And so determinant of A is, the first term is, so this one is even, this is plus, this is minus, this is even, this is odd. So the first term is corresponding to an even transposition, so it will have plus sign, and then I take a1 and where 1 goes, a1, 1, times a2, 2. And here I can see that sigma identity takes 1 to 1, 2 to 2. And then I take another permutation, which is transposition, so it has minus sign, and I write down a1, 2, a2, 1, because sigma of 1 is equal to 2, sigma of 2 is equal to 1. And so in this way we get the formula which was mentioned before, AD minus BC. So at least this agrees with what I wrote down before. So okay, so now let's think a little bit in general. So how to think about each of these terms? So imagine for a second that you have a chessboard. So imagine you have a chessboard. I hope some of you have played chess. And let's suppose it is, say, 5 by 5, which doesn't matter. And then imagine I have a rook. So remember, a rook is something which can move in straight lines, horizontal or vertical. And then, of course, if you have played chess a little bit, you know that sometimes a rook can beat another rook if they are in the same column or row. And so one can ask, okay, so how many ways are there? So let's suppose it is n by n chessboard, and one can ask how many ways are there to put n rooks so that no two are in the same column or row. So, for instance, I can put a rook in column 1 and row 2. I can put a rook in column 2 and row n. Sorry, 1, 2, 3, 4, 5. Then I can put a rook, say, here. Then I can put a rook, say, here. And then the last one is completely determined because there is only one row and only one column, which are not containing a rook now. So this one is an example of a rook decomposition. Okay, so the answer is how many ways are to put n rooks so that no two beat each other? And the answer is, of course, n factorial. And the reason is very simple, because definitely we know that we have n rooks, and all of them will be they will occupy each column and each row, just because there are n of them, and every two are in different columns and different rows. And then we can just associate to such a decomposition. It is in bijection with permutations, because you can associate a permutation to such positioning of rooks, sigma, where I put 1, and here I put, so 1 corresponds to the first row, and then I say in which column the rook stays. So 1 goes to sigma of I is the column in which the rook in row I stays. And in this way I get a permutation. So let's just look at it. So okay, so column number row number 1, column number 4. So 1 goes to 4, 2 goes to 1, 3 goes to 5, 4 goes to 3, and 5 goes to 2. So we get a permutation, and this is clearly a bijection. You can think of this positioning of rooks as a graph of a permutation, because basically a permutation is a bijection from a set with 5 elements to itself, and so you can just think of it as, if you think of it as a map, so this is just a graph of this map. 1 goes to 4, 2 goes to 1, 3 goes to 5, 4 goes to 3, and 5 goes to 2, but you should think of it flipped, basically. So these are exactly the terms in the matrix from which I should take my variables. So for instance, for this 2 by 2 matrix, there are two ways to position rooks, like this and like this. And this gives you two terms. So basically, you should think of this as a big chessboard, and every term here corresponds to some positioning of rooks, and sign corresponds to whether the corresponding permutation is even or odd, and then you add all n factorial terms. So let's do the size 3 by 3 case now. This is very important. So this is the only one where I remember formula by heart, but of course you can write it down for any n. It just becomes a little bit messy. So A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, so let me just write down 6 terms here. Each of them corresponds to some permutation, some positioning of rooks, and some sign. So, okay, let's first draw the rook positioning. So let's suppose I do this. Of course, this is a permutation 1, 2, 3 goes to 1, 2, 3, and the sign is plus. So, okay, now I want to erase something. Let me erase this part so that I will be able to write down the formula here. Okay, so this term gives me in determinant of A, I get the term A11, A22, A33. Then another position of rooks is I can do the first two in different order, and the third is here. So this picture. And this is a permutation 1, 2, 3 goes to 2, 1, 3, and the sign is minus because it is a product of one transposition, or because if you draw a diagram it will have just one crossing. So we get minus A12, A21, A33. Perfect. So next term. Okay, what else can I do? So this is the only two ways to put this rooks if I know that the third one is in the third column. But let me now move it somewhere else. Let's suppose it's here, for instance. And then we can do this one. So the permutation here is 1 goes to 1, 2 goes to 3, 3 goes to 2. The sign is again minus. And so we get minus A11, A23, A32. So then there is another one where I do this. And the permutation here is 1 goes to 3, 2 goes to, sorry, 1 goes to 2, 2 goes to 3, 3 goes to 1. And it has plus sign because it's actually, so if I draw the diagram, it will be 1, 2, 3, so two crossings. And so I get a term plus A12, A23, A31. Beautiful. Okay, and finally I can put the last rook at the top corner, and then there are again two options. So this one, and the very last one is this one. And so this permutation is 1 goes to 3, 2 goes to 1, 3 goes to 2. And this one is 1 goes to 3, 2 goes to 2, and 3 goes to 1. So this one is definitely odd, and this one is even. So then I get minus A13, A22, A31 plus A13, A21, A32. And this is the expression. So it is complicated. It has 6 terms. It is polynomial in 9 variables. And it is absolutely remarkable that this matrix A is invertible, if and only if determinant of A is not 0. So we will see it a little bit later, but basically if you want to check whether a 3 by 3 matrix has an inverse, you need to compute this complicated expression, and then you see whether you get 0 or not. Okay, so this is what is a determinant. And also, sometimes it is very convenient to think about it as determinant of a collection of vectors, where vectors v1, v2, and so on, vn are just vectors, so these guys are columns. So remember, when you have a matrix, you can think of columns as vectors in Fn, and then basically a matrix becomes the same thing as a collection of n vectors. And so sometimes I will write this instead of this matrix. Of course, you can ask me, why don't I take rows instead of columns? But the answer is actually you can do either. The determinants are equal to each other, and we will prove it in the moment. Properties of the determinant. So there are lots and lots of properties which helps to compute them really easily and understand how they behave and so on. So I will talk about the most important ones, but there will be still quite a bit. And all the proofs are a little tricky because we need to work with permutations. So the first one is that determinant of a matrix A is the same as determinant of A transposed. So when you flip the matrix, then determinant does not change. Okay, let's prove that. So I still think about my A11 up to A1 and n matrix. So I know that determinant of A is just the sum over all permutations sigma in Sn, minus 1 power sigma A 1 sigma of 1 to the d a n sigma of n. So you need to remember how to write it really quickly. That's a complicated expression. Okay, so let's suppose that A transposed is equal to B, and this B has coefficients bij, for I and j being from 1 to n. So then I know that bij is the same as AJI. So this is simply because this is what transposition does, right? You exchange columns and rows. And then determinant of B, of course, is just the same sum, but now, so also we have sigma over Sn, and now we do minus 1 power sigma, and I do B1 sigma of 1 to the B n sigma of n. Okay, so on the other hand, this equals to, obviously, sum sigma Sn minus 1 power sigma, a sigma of 1, 1, and so on, a sigma of n, n. Okay, so this looks very complicated because it doesn't look at all like that. So let's try to think. So what is a sigma of 1, 1, and so on, a sigma of n, n? Can we compute it in some other way? So the answer is that it is an observation, which is very easy, but somehow a little bit fun, that a sigma of 1, 1, and so on, a sigma of n, n, is the same as a1 sigma inverse of 1 up to an sigma inverse of n. So why this is the case? This is the case simply because, I mean, of course, the statement that the products are equal follows from the fact that these numbers and these numbers are just the same numbers, just in different order. And the reason is, let me explain why this is the case. So we know that, for instance, so let's take some. So this follows from the fact that the set of numbers a sigma 1, 1 up to a sigma n, n is just the same set of numbers as a 1 sigma inverse of 1 and so on, a n sigma inverse of n. Then, of course, if you have two collections of n numbers which are the same sets, just in different orders, their products are the same. And why this is the case? I mean, so proof is like that. So let's take, for instance, some element here. So ai sigma inverse of I, of course, equals to a sigma of so we know that I is equal to, some sigma of j. I mean, because sigma is a bijection. So then, actually j is just sigma inverse of I. So I is equal to sigma of sigma inverse of I, comma, sigma inverse of I. And so you see that actually this equals to a sigma of j, for some j. So this means that this element lies inside this set. So we proved this equality. And of course, similarly proves this equality. So basically, if you think a little bit about that in a different language, so we know that, for instance, for some number I, sigma of this number equals to 1, because sigma is a bijection. When you will find that you will have some here, sigma 1, and then something, and something should be the number which went to 1 under sigma, which is, of course, sigma inverse of 1. And so you see that this number is there. So in this way, we see that two guys are equal, so these two monomials are the same. And so it means that determinant of B equals to sum over sigma in Sn minus 1 power sigma. And then we just write instead of this monomial, A1 sigma inverse of 1 up to a n sigma inverse of n. So that looks almost right, because now we sum up overall permutations, except we put here sigma inverse. But denote the sigma inverse by tau. And also notice that sine of sigma is the same as sine of sigma inverse. So sine of sigma is the same as sine of sigma inverse. We proved it last time. That's because sigma composed with sigma inverse is identity, so it's even. So sine of sigma plus sine of sigma inverse is even. So both of them have to be the same. And so it means that actually here we have sine of sigma inverse, and here we do the same monomial. So everything is exactly like in the determinant of A formula, but with sigma inverse instead of sigma. So we can write it as sum. And here stays just all permutations. So let me just say so sigma inside Sn, and then I have minus 1 power tau, A1 tau of 1 up to an tau of n. But now, when you sum up over all permutations and then plug in its inverse, it's absolutely the same as just to sum over all taus. So this is just the same sum over all tau in Sn, and then the same thing here. And the reason is just because when you, instead of each permutation consider its inverse, you just relabel the set of Sn. For every permutation there exists a unique inverse, because inverse inversion of a permutation is a bijection from Sn to itself. And so that's why basically we have absolutely the same summation over the same terms, just with sigma renamed by tau. And so this is determinant of A. Okay, I'm sorry for the marker. I will get a new one in 1 second. So in this way, we see that basically after we relabel permutations, instead of sigma, we write sigma inverse, the monomial will go to this transposed monomial. Signs are the same by the theorem we proved last time, and so we get that these two expressions agree. And we have proven the first property. Okay. So now let's discuss how the determinant changes when we do elementary operations. So, 2. Elementary operations. So I will do them with columns, but of course, since we already know that determinant of a matrix is the same for matrix and transposed, the same is for rows. So all properties are the same. So properties are the same for these elementary operations for rows and for columns. And let's see what is easier. So it's definitely easier to do operations with columns. Okay, so let's do them with columns. So there are 3 elementary operations. So let's start with C1. And C1 is exchange i's and j's column. So we have a matrix, and we just take i's columns and j's columns and exchange it. And of course, we imagine that not much should change. And the fact is that this is A, and the transformation sends A to A prime. And the fact is that then determinant of A equals to minus determinant of A prime equals to minus determinant of A. So determinant changes sign when you exchange a pair of columns. Of course, there is a more general fact. You can do any permutation with columns, and then the determinant will change accordingly, but I will say it in a second. So let's first prove that. So let's take determinant of, so let's suppose we have A. So we have A ij, and we have A prime, which is this A ij prime. And we know that A ij, sorry, let me exchange not i's and j's, but A and B column. And then we know that Aij prime equals to Aij when so we exchange columns. The first index is row when J is not inside the set AB. And then we know that Aij A prime is equal to AIB, and AIB prime is equal to AIA. So the 2 columns are exchanged, and everything else is fixed. So let's prove the statement. So determinant of A prime equals to sum over all sigma in Sn, and then we have minus 1 power sigma, A1 sigma of 1 prime, A prime n sigma of n. And then notice that let's analyze what this thing is. So A1 1 sigma of 1 to the an sigma of n prime will be, of course, the same as the monomial without primes, except for two things: when sigma of something equals to a, and sigma of something equals to b. So basically, so it will be absolutely the same, except we need to exchange here. So two of the terms are different. So here is a convenient way to write it. So let's consider a new permutation. So let's look at sigma composed with just 1 second. Okay, let sigma prime be the transposition AB times sigma. Then what we know is that so the claim is that this thing equals to A1 sigma prime of 1 and so on, an sigma prime of n. So why this is the case? So let's just look at term by term. So a prime I sigma of I, of course, is equal to ai sigma of I for sigma of I not equal to a or b. So this means that all but two terms just agree exactly. And then if you take a prime I sigma of I where this guy equals to a, then we know that it equals to a IB. But simultaneously, let's see what is B. So so B is the transposition AB applied to the number C of I, sigma of I. Why? Because sigma of I is A and transposition AB sends it to B. So this is exactly a I sigma prime of I. And so the statement is true. And similarly for B. And so we get that basically these monomials agree, except now instead of sigma we take another permutation where we multiply on the transposition. But then notice that sign of sigma prime is minus sign of sigma, because if sigma was a product of an even number of transpositions, sigma prime will be a product of odd number of transpositions, and vice versa. So now we can say that determinant of A prime equals to, we have sum over all sigmas in Sn minus 1 power sigma A1 sigma of 1 prime to the An sigma of n prime, which equals to minus, and then we have sum of sigma in Sn, and now minus 1 power sigma prime A1 sigma prime of 1 and so on, An sigma prime of n. So that's because we proved this and because the sign changes. So if we write here sigma prime, we need to add minus 1 sign here. And now notice that when you sum over all permutations multiplied by AB, that's absolutely the same as just to sum over all permutations, because multiplying all permutations on AB, you just get the same set. So, so if you take a map from Sn to Sn, which just takes any permutation sigma and sends it to AB times sigma, so this is a bijection. And the proof is just because you can, for instance, multiply backwards on the same transposition. So when you do this transformation twice, you get identity map, so it's a bijection. And so the summation doesn't change, you just relabeled permutations. And so this equals to minus determinant of A. So when you change two columns, then the sign of the determinant flips. Okay, so this statement has two corollaries. So this was property 2, so corollary, so let me call it, okay, so let me call this just property 3. So if a matrix has two equal rows or columns, then the determinant is equal to 0. So that's just because we know that the proof is just flip them, so flip them, and then determinant of A equals minus determinant of A. And here is a funny trick. So honestly, this does not exactly work, because for instance, if you have your field being F2, then this doesn't prove anything. So this proof for F2, one needs a different proof. So if your field has a property that 1 is the same as -1, this proof will not work, but the statement is still true. Let me not prove it. It's actually not hard. So another property is that just if you now take a determinant and you will exchange the columns arbitrarily, so you can take vectors v1, sigma of 1, and so on, vn, sigma of n, then it just equals to the sign of sigma, minus 1 power sigma, times determinant of v1, vn. So basically, if you exchange in any ways columns, you will just take the determinant is multiplied by the minus 1 or 1, depending on whether permutation is even or odd. So why this is true, that's just by induction, because you know this is true for transpositions, and so you can now present your permutation as a product of transpositions, and then apply doing this transposition successfully to eventually prove the statement. So that's very, very straightforward. It just follows from the previous property. Perfect. So now let's discuss the second row operation. So that's property 5. So let's discuss the column 2 operation. So what is a column 2 operation? So that just, I remind you, had a matrix A, which was some matrix Aij, and now you have A prime, Aij prime. And what we do, so we just rescale one of the columns. So Aij prime equals to lambda Aij for the column j equal to some number A, and Aij prime is Aij for j not equal to A. And this is the operation corresponding to A's column. So you take A's column and you multiply it on lambda. So multiply on lambda. Okay, so here everything is really easy, because basically when you take determinant of A, it equals to sum of minus 1 power sigma in Sn, sorry, A prime, A1 sigma of 1 prime to the An sigma of n prime. And then, of course, if you think about it, so remember, this 1 sigma of 1 and so on n sigma of n is a rook decomposition, positioning. So there exists exactly one rook in the column A. So exactly one of these terms is rescaled. And so what happens is that this is the same as sum over sigma in Sn minus 1 power sigma A1 sigma of 1 to the an sigma of n, and each monomial will be multiplied by lambda. Remember, lambda is so usually in this elementary operations we take lambda not equal to 0, but of course this argument will still work. And this is just lambda times determinant of A. And corollary is that, let me call it 6, is that so if a row or column of A equals to 0, then determinant of A is 0. By the way, remember, later on we will see that determinant is 0 or not, depending on whether your numbers here, your vectors here are linearly dependent or not. And properties 3 and 6 just means that here we say that if two vectors are the same, they are linearly dependent. And this tells you if you have a 0 vector here, the vectors are linearly dependent, and we know both of these facts. So, okay, 7 is a little bit, let me forget for a second about row operations. I will talk about it in a minute. So let's take A being diagonal. So what it means A just equals to d11, d22, and so on, dnn. Everything else is 0. So suppose it is just the diagonal matrix. So then determinant of A is just d11 and so on, dnn. And the proof is just because, so proof is because any monomial A1 sigma of 1 to the an sigma of n contains 0 if sigma is not the identity. So if you take any monomial where sigma is not an identity, there will be a term where I and sigma y are different, so you will get 0, and so monomial is 0. So out of the whole sum in the determinant, you just get the term for sigma being identity. Here you have 1, and here you have the product of elements on the main diagonal. So in particular, if you take the identity matrix, the determinant of the identity matrix is 1, and determinant of 0 matrix is of course 0. That follows from 6, for instance. Perfect. So now we know that we can flip columns, flip rows, we can multiply or scale rows or columns. We have some additional properties. We know how to compute determinant of a diagonal matrix. So finally, let's prove the way how it behaves under the third column operation. Okay, so now property 8 probably. So let's do C3. So third column operation is as follows. So let's just write in terms of vectors. So suppose A was a matrix consisting of columns v1 up to vn, and then A prime will be v1 prime, vn prime. So we choose some number lambda inside F, and we choose A and B from 1 to n, which are distinct. And then vi prime is equal to vi for I not equal to A, and va prime equals to va plus lambda vb. Of course, if I just add everywhere here some index, I will get the property for the matrix elements. Okay, so the claim is that then determinant of A is determinant of A prime. So these guys agree. And the proof is quite simple. So, so in terms of Aij, I know that Aij prime equals to Aij for j not equal to the number A, and Aij prime equals to Aij plus lambda Aib for j equal to A. So this is how the matrix changes. And then let's look at monomial. So if you take monomial A1 sigma of 1 to An sigma of n prime, then of course, so we know that all of them will be the same as without primes except one. So it equals to A1 sigma of 1 to then we will have one term where j equals to A, and this will be A1 A. And here we'll get A1A plus lambda A1B, and then A n sigma of n. So this is for the case, so this is for, so this is, if you want, in terms of sigma, this will be some sigma of, sorry, sigma inverse of AA. Sorry, so this term is A sigma inverse of A plus lambda A sigma inverse of A B. Okay, so this we can expand as a sum of two terms. So one of them is A1 sigma of 1 to A sigma inverse of A sigma of sigma inverse of A to A n sigma of n, and this is of course exactly the term as in the usual determinant. So this is just, if you want, you can just plus A1 sigma of 1 to then here we have A lambda A sigma inverse of A B to A n sigma of n. Okay, so let's think about it. So of course this is the same term as in the determinant of A. And this guy is the same term as in the matrix, which I will denote A prime, where this matrix is just exactly the same matrix as our, except so it is V1 to the VB to the VB Vn. So this is the same matrix. Instead of VA, we just substituted it with VB. So the idea is that when you do that, so in this monomial you have two repeating terms. You have A sigma inverse AB, and you will have it again because you still have somewhere the sigma inverse AB term later. And so what happens is that actually then when you sum up overall permutations, you get that determinant of A prime is equal to the determinant of A plus lambda times this determinant, sorry, A2 prime, let me call it, plus lambda is determinant of A2 prime, where this A2 prime is a matrix where you just now have two equal columns to VB. So, and this equals to determinant of A, because this guy has two equal columns. So this is the idea. So basically, again, if you take a formula, if you take its general term, just any term, you can write it down as a sum of two terms. One is exactly as in the formula for the determinant of A, and another is exactly as in the formula for a determinant of a matrix, where you have instead of your A column, lambda times B column. And this is, of course, 0, because you can take lambda out by column operation 2, and then you have two equal columns. So that's why it's the same as determinant of A. Okay, so what do we see? So third column operation and equally third row operation don't change the determinant. First column and row operations flip the sign. Oh, by the way, guys, you wanted to see Neville. Oops, this is one. Okay, and so this is determinant. Sorry, what I was talking about. So determinant flips the sign when you multiply on a transposition. When you exchange a pair of columns or rows, determinant is the same when you transpose the matrix. Determinant is rescaled by lambda when you multiply column or row on lambda. And determinant does not change when you take one column and add it to another rescaled by number, or do the same with rows. Perfect. So this is, of course, this gives a way to quickly compute determinants. For instance, if you want to compute a determinant of a matrix, let's say 2, 2, 0, 1, 0, 1, 0, 2, 0, you can just easily, for instance, first let's take 2 out and another 2 out. Just this is operation C2 applied to first and third column times determinant. So determinant of the matrix where now I have 1, 1, 0, 1, 0, 1, 0, 1, 0. And then, for instance, I can subtract the last column from the first one. That will not change, so we get 4 times determinant of 1, 0, 1, 0, 1, 0, 0, 1, 0. And similarly, I can subtract the first column from the second. I get 4 times determinant of 1, 0, 0, 0, 0, 1, 0, 1, 0. And now I can compute the last two columns, and it flips signs. And I get -4 determinant of the identity matrix, which is -4. So using row and column separations, you can easily compute determinant. You just need to be careful. So when we're computing ranks, you don't need to remember the sign, you don't need to remember which numbers you took out. But here you need to be careful. So every time you apply operation C1, you change the sign. Every time you apply operation C2, you get some additional number you take out of your matrix. But other than that, computing determinants using this approach is quite easy. Okay, so now we can prove some corollaries of all this story. So theorem. So the following are equivalent. So we have some matrix A. So the first statement is determinant of A is not equal to 0. The second is A is invertible. Third is columns of A are linearly independent as vectors in Fn, and 4 is rows of A are linearly independent. So these are all the same thing. Maybe 5 is a system of equations A11, x1 plus a1n xn equals to 0, an1 x1 plus ann xn equals to 0 has only 0 solution. Okay, so these are all the same things. And again, so the idea is determinant helps you to check all of that, whether a system of equations has a solution, whether vectors are linearly independent, whether a matrix is invertible. So let me prove it. So proof is honestly very, very simple now. So let's just recall everything here is trivial, so except about one. So we know that, for instance, we know that, let's see. So if the matrix A is invertible, so 2 implies 5. System of equations has only 0 solution, and the reason is because your equation is actually just A times a vector equal to 0, and so matrix is invertible, then of course V equals to A inverse times 0, which is 0. So 2 indeed implies 5. So 5, sorry, maybe 6 is linear operator given by A is an isomorphism. Okay, so 5 implies 6, for instance, because of course AV is 0, has only 0 solution. It means that then kernel of A is 0, but then remember, by rank nullity theorem, then by rank nullity image is the whole space, and then of course A is an isomorphism. But for A being an isomorphism, that's equivalent. So this is, of course, 6 is just equivalent to the fact that A of E1 up to AEn are linearly independent. So this is just the same thing, and so we have that 2 implies 5, 5 implies 6, 6 is equivalent to the fact that A of E1 up to A of E1 are linearly independent. So also, so A is invertible, yeah, and of course 6 implies that A is invertible, just because if so 6 implies 1. Just because we know that 6 implies 1, just because we know that if a linear operator is invertible, then the matrix, sorry, 2, the matrix is invertible. And then of course we know that 3 is equivalent to, so we know that A is invertible if and only if A transposed is invertible, simply because if you take A transposed inverse, this will be just the inverse to A transposed. And so this is why, of course, any statement for rows is equivalent to any statement for columns. So we see that everything is equivalent to each other except 1. So let's prove that 1 is equivalent to 2. So we need to show that 1 is equivalent to 2. And this is really now not very hard, because so we know that so we can transform A to the form 1 1 1 1 1 0 0 0, where the number 1 is a rank of A. by transformations C1, C3, R1, R3. So remember, you can always move a matrix to this form where you just have ones on diagonal and everything else is 0, and the number of ones is the rank. And then notice that if A and A prime are related by a sequence of elementary operations, then determinant of A equals to 0 if and only if determinant of A prime equals to 0. And the reason is because every operation multiplies determinant by a non-zero number. So remember, operations 1 and 2 multiplied by -1 and lambda, and operation 3 doesn't change it. So that's why when you do the separations, your determinant will just multiply on some number, and if this number, since this number is always not 0, your determinant was 0 or not for A, it will be also 0 or not for A prime. So the same. So determinant being 0 for A is equivalent to determinant being 0 for A prime. But then, of course, so it means that determinant of A is equal to 1 times 1 times 1 R times, rank times 0, 0, 0, 0. So it equals to 0 or 1, and 0 is if rank is less than n, and 1 if rank is equal to n. But I remind you that rank is exactly dimension of the image, and so dimension of the image for a map from a space to itself is equal to n if and only if the map is an isomorphism, and so we get the determinant of A is equal to 0 to not equal to 0 if and only if the dimension of the image is equal to n. So if and only if the operator is an isomorphism, and so then 1 is equivalent to, say, 6. So 1 is equivalent to 6. And again, I'm using here every time this very fundamental fact that if you have a map from a space to itself or a square matrix, then so its kernel is equal to 0 if and only if its rank is equal to n. So dimension of the so the map is surjective. So linear operator is an isomorphism if and only if it is injective, if and only if it is surjective. In general, that's not the case for arbitrary, more general maps between spaces of different dimensions, but if dimensions of the space are the same, then it is true. Okay, so we have proven this theorem, and again, everything here is more or less obvious except the first one, and I just did it for completeness because it's really important stuff. So my next goal is to explain another approach to computing determinants using what's called minors. That's very important, and that's a little bit of a different topic. So I will do that now.